In this video, I will try to explain why we divide by n-1 instead of n when we calculate the sample variance. In a previous video, I showed this based on simple simulations. However, in this video I will focus on a mathematical proof of why we divide by n-1. Note: before you watch this video, I recommend that you first watch my video about the expected value, because I will here assume that you are familiar with that concept. This is how the sample variance is calculated. Remember that in statistics, the variance is a measure of the spread of the data. We usually use lowercase letters when we refer to a sample and uppercase letters when we refer to a random variable. X sub I is the values in our sample, whereas x bar is the mean of those values. Suppose that we have a population of 1 million people and that we like to know the mean body height and the variance of the heights of all these people. Since it would be too much work to measure the heights of all the 1 million people in a population, we can instead take a sample of, for example, 4 individuals and measure their body heights. The average height of these 4 individuals is 169.5 centimeters. Let's calculate the sample variance. We plug in the sample mean and the body height of each person, as well as the sample size, which is 4 in this case, because our sample includes 4 individuals. If we do the math, we see that the variance is about 21.67. Let's put this value up here. Suppose that we now take a new sample of 4 individuals. Due to chance, this sample happened to include people with a larger spread in the body height. If you compute the variance of this sample, we see that it is much bigger than in our previous sample. We have now computed the variance from 2 samples. Suppose that we would repeat this process 10,000 times, so that we have 10,000 sample variances. If we calculate the mean of all these 10,000 sample variances, we will get the value that is close to 49. In this example, we happen to get the value that was equal to 48.9879. This is how we calculate the variance and the mean of a sample. And this is how we calculate the corresponding thing if we have measured the whole population. Note that s squared and sigma squared are just symbols for the variance that illustrate that the variance is the square of the standard deviation that is denoted by s or sigma. The sample mean and the population mean are denoted like this. The only difference in these two equations is the notation of the sample size. Little n represents the sample size, whereas big N denotes the population size. When we calculate the population variance, we know the population mean, which means that we divide by n instead of n-1. This is due to that the data points will generally be closer to the sample mean compared to the population mean, as I showed in the video that was based on simulations to explain why we divide by n-1. When we have just by dividing by n-1, this is called Besel's correction. Now, suppose that we would measure the height of all the 1 million people in this population. If we would calculate the population mean and the population variance based on the 1 million people in this population, we now know the population variance and the population mean. We see that the mean of the 10,000 sample variances is approximately equal to the population variance. We therefore say that this formula gives us an unbiased estimate of the population variance. If we instead would have divided by n instead of n-1, the mean of the sample variances would be much lower than the population variance, which is the one we try to estimate. So, if we divide by n instead of n-1, this will result in a biased estimate of the population variance. Remember from the video about the expected value that E denoted the expected value, which can be seen as the mean of a large number of samples. This means that if we would compute the mean of a large number of sample variances based on random samples from the population, as we did here, that mean value will be equal to the population variance. So, if we had taken an infinitely large number of samples from the population instead of just 10,000, we would have got a value that was exactly equal to the population variance of 49. I will now show mathematically why we divide by n-1. We can begin to put n-1 to the left, like this, because that will not affect the mean value of the sample variances. Let's put the equation up here as a reference. We will now focus on rewriting this part. We therefore place it here. Let's expand this square by multiplying the terms in the two brackets, so that we get the following terms. Then we move the summation notation around each term, since the total sum of the terms is the same as the sum of the individual terms. To understand the individual terms, we will here use the following sample of 4 individuals with a mean height of 169.5. This term means that we will sum the square of the 4 values in our sample. If we would compute the corresponding calculations for this term, we see that we can pull out the mean and the 2 from the summation, like this, because that will not change the result. If we compute the corresponding calculations also for this term, we see that we can calculate the same thing simply by multiplying the sample size by the squared mean. We can therefore simplify this term to n times the squared mean. The sum of the observations can also be expressed as the mean of these 4 observations times the sample size. We can therefore substitute this summation with n times the sample mean. This term can be simplified to 2 times n times the square of the sample mean. We can now add these two terms, so that we are left with just n times the square of the sample mean. Let's see if what we have here results in the same as what we have here, based on our example data. The sum of the square differences between observations and the mean is 65, which we also get with the modified equation, because the sum of the squared observations minus 4 times the squared mean is also 65. This is therefore basically just another form for the sum of the square differences between observations and the mean. E denotes the value we would expect if we would compute the mean of the sum of the squares from a large number of samples. For example, the sum of the square differences based on the first sample is 65, whereas the sum of the square differences based on the second sample is 249. If we would continue to draw, for example, 10,000 samples and calculate the mean of the sum of the square differences, that mean value will be equal to about 147 in this example. If we divide this value by the sample size minus 1, we see that the mean of all these sample variances is equal to the population variance that we calculated in the beginning of this video. It turns out that we will get the same mean value if we first calculate the mean of the sum of the squared observations minus the mean of n times the squared sample means. We can therefore formulate an equation like this, where we will compute the expectation of each term. Since the expectation is a linear operator, we can move e to the right-hand side of the summation notation. It is important that when we consider e, we should think of it as the mean of a large number of samples. A large number of samples is thousands of samples. Although we would need thousands of samples, we will here illustrate the idea with just 3 samples. Let's say that we would sum the squared observations for each of these 3 samples. and calculate the average of these sums. That would be the same thing as summing like this. The expected value of the sums is therefore equal to the sum of the expected values. We can also pull out n from the expectation, like this, because if you compute n times the square of the sample means, the mean of these values will be exactly the same as if we would first calculate the mean of the squared sample means, and then multiply this with the sample size. We can therefore focus on this expression. According to the expectation rules that I will show you later on, the expected value of a squared random variable is equal to the variance plus the squared mean of that random variable. Note that I here use uppercase X because we now talk about a random variable and not a sample. Similarly, the expected value of the squared mean of a random variable is equal to the variance divided by the sample size plus the squared mean of that random variable. Let's plug in this here and this one here. If we now multiply these terms with n, we see that we can cancel these n's. Since sigma squared and mu squared are just constants, the summation of n constants is simply equal to n times those constants. For example, the summation of 4 eighths is equal to 4 times 8. If we remove the brackets, we see that we can now cancel these terms, so that we are left with the following two terms, which can be written as sigma squared times n minus 1. If we now replace this part of the equation with sigma squared times n minus 1, we'll get the following equation, where we now can cancel n minus 1 to show that the expected value of the sample variance, which involves n minus 1 in the calculation, is equal to the population variance. We have therefore shown that by dividing by n minus 1 gives us an unbiased estimate of the population variance. We will now try to understand these expectation rules. Let's put them up here. From the previous video, we know that the expected value of a discrete random variable can be calculated like this. The results from rolling a die can be seen as the discrete random variable. For example, the expected value of a fair die can be calculated by multiplying all possible outcomes with the probabilities of these outcomes. If we do the math, we see that the expected value of a fair 6-sided die is 3.5. Similarly, the expected value of the squared observations is about 15.16667. Let's save our expected values here. These are the possible values that our random variable can take, and these are the probabilities to get those values. The expected value corresponds to the mean of the random variable. The variance of the random variable is given by the expected value of the squared differences between the possible outcomes and the mean, which in this example is equal to about 2.917. The variance of the random variable can be denoted as sigma squared, or like this. We therefore know that the variance of a random variable can be calculated as the expected value of the square deviation from the mean of x. If we do some math, we see that the variance of x is equal to the expected value of the squared observations minus the square of the expected value. We can therefore express the variance also like this, or like this. This can be rearranged like this. We have therefore shown that the expected value of the squared observations is equal to the variance plus the squared mean. If we plug in the variance and the mean and do the math, we see that we get the mean of the squared observations. We will now see how to derive the expected value of the squared mean. the variance of the mean of a random variable can be denoted like this. This is how the mean is calculated. Suppose that we would roll a die 2 times and calculate the mean of these rolls. We would therefore sum the values and divide this sum by 2 because we have rolled the die 2 times. Then we repeat this process 2 more times, so that we have 3 mean values. We then calculate the variance of these means, like this. Note that n in this formula represents how many sample means we have, whereas n in this formula represents the sample size used to calculate these means, which is here equal to 2, because we calculated the mean based on 2 rows. We can take out 1 over n, like this, which then becomes 1 over n squared, because the variance involves squaring the differences. If we would calculate the variance of the sums, we should instead calculate the sum of the 2 rows, and plug in these in the equation, minus the mean of the sum of the values from 2 6-sided dice, which is 3.5 plus 3.5, and then divide by 3, because we have 3 such sums. Finally, we multiply with 1 over 2 squared, because our sample size to calculate the sums is 2. We see that we get the exact same variance. If we would repeat these rows thousands of times and calculate the variance of all these means, we would get the value of about 1.458. We can move the notation for the variance inside the summation, because the sum of the variances of 2 individual rows that we calculated previously to about 2.917 divided by 1 over n squared will result in the exact same variance. The variance of a random variable is equal to sigma squared. The sum of sigma squared is equal to n times sigma squared, because sigma squared is just a constant. If we cancel the n's, we see that the variance of a large number of sample means is equal to the variance of the random variable divided by the sample size. This is what we discussed in the video about the expected value, where a sample mean from a large number of rows will approach the expected value. The variation of the sample means becomes smaller and smaller when the sample size increases. We therefore know that the variance of a large number of sample means is equal to the variance of the random variable divided by the sample size that was used to calculate the means. If the sample size becomes infinitely large, the variance of the sample means goes to 0. We have previously seen that the variance of x is equal to the expected value of x squared minus the square of the expected value of x. The same is also true for the variance of a mean, which is equal to the expected value of the squared mean minus the square of the expected value of the mean. We can rearrange this equation like this. We then substitute the variance of x bar by sigma squared over n, and replace the notation for the expected value of the mean by mu. We have therefore shown how to derive this equation. Finally, let's try to understand what this equation actually means. Suppose that we would roll a die 2 times and calculate the mean of these 2 rolls. Then we continue like this many times. If we would repeat this process so that we have 1000 mean values, they will be distributed like this. The expected value of the means is equal to the mean of the random variable, which is here equal to 3.5. However, if we would square these mean values, we might think that the expected value of the squared means would be equal to the square of 3.5, but it is actually here equal to 13.7. This is due to that squaring large mean values will move them further away from the mean, compared to squaring low values. Let's compute the expected value of the squared means with this equation. If you plug in the variance of the random variable that represents the rolls of a die, and the sample size we use to calculate the mean values, and the mean, and do the math, we see that the equation gives us the correct mean value of the squared mean. This was the end of this video about why we divide by n-1 when we calculate the sample variance. Thanks for watching.